Last class I was saying that those governing equations will emerge from the laws and axioms of classical mechanics that we are already aware of. Law of conservation of mass, Euler's first axiom, and first law of thermodynamics. These are the equations that will help us get governing equations for these fields. But before I start deriving the equations, we need to learn some new definitions and some concepts that follow those definitions. These are the new things we want to learn: a control surface, a control volume, an entity. Now, entity is a word which can have many meanings. In my class, it will have some meaning, and that I would like to explain. What do I mean when I say the word entity? Advective flux of an entity through a control surface, and the net advective flux of an entity into a control volume. Okay, advective flux through a control surface and net advective flux of an entity into a control volume. What do all these things mean? Let's start with control surface. A control surface is an imaginary surface within the flow domain or coinciding with the boundary of the domain. So if this is the flow domain, I can imagine a plane surface like my palm. Imaginary. Does it exist? चल रहा है अभी, बीच-बीच में blink कर रहा है. हाँ, 5 मिनट रुक जाओ. So I can have a control surface like this, an imaginary surface in the flow domain or coinciding with the boundary of the domain. So there is air in this room. This is the fluid domain. This is a solid boundary. I can have a control surface coinciding with that also. Now this control surface is imaginary and it is transparent. Fluid particles can pass through it. Okay. But I want to have this concept because it will help me derive something, derive equations. Okay. Now the surface, the surface of this so-called control surface, it does not change its shape or size with time. It's not allowed to. Once you choose a control surface, its shape, size has to remain the same at say 2 time instants. All right. A control surface, so I'm using this acronym CS. A control surface may be closed or open. This is an open control surface, right? I have shown here another example. This is a hemispherical shell or a surface. This is also open. What would be a closed surface if I consider full spherical surface, right? So it may be closed or open. It may rotate or translate with respect to the reference frame in context if we want to make it happen. If my derivation of something requires this control surface to be rotating, translating, I can have that. Okay. However, the derivations that we will make of the basic equations, in all those cases, control surfaces will be stationary. Stationary with respect to whom? With respect to this man here. Will not rotate, will not translate, will not change its size, will not change its shape. While the fluid particles keep moving around it, passing through it. So fluid particles I am not putting any constraint on. Control surface is in my control. In fact, that's why it's called a control surface. You control, not the fluid. Now, if you have a control surface like this, we associate two sides of the control surface. Like I have shown here, side A and side B. And that is possible for open surfaces as well as closed surfaces. right? If it is fully spherical, inside, what we call inside will be side A, what is outside will be side B. Yeah. Definition, all this definition. Control volume. Control surface, control volume. This is also imaginary. It is an imaginary volume in the fluid domain, like what I have shown here. This is what I call as control volume. I've written here control volume V, this bigger thing. This whole thing is the control volume. Now, inside that control volume, for derivation, sometimes we will consider an infinitesimal part of that control volume, which I am denoting by dV. And at a given time, that may be at a position vector x. We will keep using this figure on many slides. But right now, what I'm calling as the control volume is the whole big thing. And mind you, this is not small. It can be of any size. Same goes for control surface as well. I did not say it was small. You can have a control surface as big as possible, as big as you want. Depends on what you want to do with it. All right. Again, just like control surface, a control volume may be fixed to the reference frame in context, or it may be moving. When I say moving, I mean translating as well as rotating by a user specified value. Okay. For all our derivation, control volumes will be kept stationary with respect to that man, reference frame F. Shape and size of the control volume are also supposed to be fixed at all times, like a control surface. Right. Last point here, I've already mentioned dV is a small part of this. Like control surface, the walls of the control volume are transparent. In fact, the surface that encloses the control volume is actually a control surface, right? And it should be what kind of a control surface? Open or closed? Closed. So the control surface of a control volume is always closed. However, all control surfaces need not necessarily be closed. Fine. Entity. As I said, it has many meanings. For me, this is what it will mean. When I say entity, what I mean is kind of a placeholder for me. In the absence of any other appropriate word, I use the word entity. When I mean to say, in a general way, mass of fluid, I mean to say mass of fluid can be called as an entity. Momentum associated with the fluid can also be called an entity. Total energy associated with fluid can also be called an entity. When the entity is mass, unit will be of course kg, momentum kg meters per second square. And if it is total energy, it's going to be joule. So the units of the entity will change with context. Now, talking about total energy of the fluid, there are two parts. There are two contributions that come when I say total energy. One is the kinetic energy of the fluid, and the other is the internal energy of the fluid. Right? In fact, I can consider sometimes during my derivation, I may consider this itself as one entity, kinetic energy, or internal energy as another entity. Sometimes I will combine them and call that as total energy, and that will also be an entity. The table that I'm showing on the right hand side, I have all these possible entities listed on the first column. And then I am writing what would be the entity per unit mass of the fluid. So if I give you a handful of fluid like this, it has some mass, kg. It has some momentum. Would you agree with me? It has some momentum. M times velocity vector, and it will have certain amount of energy. But then while doing derivations, I would not be so much interested in how much is the value of mass here, but I may be interested in how much is the mass per unit volume of the entity. Similarly, momentum per unit volume and moment energy per unit volume. Okay. Sometimes I will talk about not mass, not momentum per unit volume, but momentum per unit mass of the entity. Right, per kg. Energy, total energy associated with the fluid per unit mass of the fluid. Okay, those things I have listed here. So if entity is mass, what would be entity per unit mass of the fluid? Well, that will be unity, right? Kg per kg. But what will be entity per unit volume of the fluid? That would be density, right? Unit will be kg per meter cube. This is the symbol we will use. Now, if an entity is momentum, and if I am talking about momentum per unit mass of the fluid, will you accept that? Vxt is momentum per unit mass of the fluid. But if I talk about entity per unit volume of the fluid, that will be the product of local density and local velocity vector. Momentum per unit volume. Okay. If I talk about kinetic energy as the entity, the kinetic energy per unit mass will be this. If there is any mistake, do let me know, because I wrote it just yesterday, so there may be some mistakes. So scrutinize. And that reminds me to make a comment here. See, all the notes that I give you, they are not legal documents, and they are also not proof written, proofread. 2-3 दिन पहले मैं बनाता हूँ और दिखाता हूँ. क्यों दिखाता हूँ? I want to help you. Why do I upload? Because I want to make it accessible. Onus is on you to scrutinize what I write is correct or not. Do not create a situation that after a quiz or an exam, you come and tell me you have written some wrong answer and you say that, sir, आपने ही ये लिखा था, इसलिए मैंने ये गलती की है, आपको marks देना पड़ेगा. I am disclaiming, I am not responsible for that, because this is not a legal document. These are all to help you, but your job starts after getting this to learn from it, scrutinize and find errors. मैं तो हमेशा बोलता हूँ मुझे बताओ कहाँ गलती है. I will be very happy to accept. Okay, so don't bring that argument. Instead, scrutinize when you read. And if you let me know the errors, I would be very happy, because that helps me communicate to the students, all the class. All right, so this is kinetic energy per unit mass. And if I have to talk about kinetic energy per unit volume, this will be the quantity. You agree with that? Local V dot product half multiplied by rho. Local rho. I have not written here rho because I was running out of space, but whenever I write rho, it actually means rho at x comma t. It is an Eulerian field. So this is also at xt. This is also at xt. It's got to be. You cannot take density of this point at this point multiplied by velocity at this point and say that this is the momentum per unit volume of this point or that point, right? Local. Internal energy. What should be the expression for internal energy per unit mass? You have learned this sometime in class 12. For substances, various substances. Any recollection? Has to do with something called specific heat capacity. At constant volume, did you read something like that? And at constant pressure. There are two types of specific heat capacity. Specific heat capacity at constant volume and specific heat capacity at constant pressure. For liquids, it's irrelevant. constant pressure and constant volume both are approximately the same. For gases, they may be different. However, whether it is liquid or gases, the internal energy is always, what is T? Temperature. Unit joule per kg. So if that is the expression for internal energy per unit mass of the fluid, what should be the expression for internal energy per unit volume of the fluid? Sorry, density. Yes. Yeah. And if I have to talk about total energy per unit mass, then you just add the previous entries. Okay. Now on my next slides, I will refer to this quantity more than actually the other quantity. And I want to have a placeholder for whatever is appearing here. That placeholder for me is a tensor phi, which is an Eulerian variable, and this is entity per unit volume. Placeholder. Some derivation I will do generally, taking it to be a general entity, and that's where I will use phi vector. Phi tensor. Now this phi tensor, even I am putting this as a tensor, this can in some cases become a scalar, depending on what the entity is. Do you see that happening there? For what entity this general placeholder phi under bar becomes a scalar? किसके स्केलर बनेगा? मोमेंटम के लिए स्केलर है, इंटरनल एनर्जी के लिए है रो सीवीटी, टोटल एनर्जी के लिए भी है, काइनेटिक एनर्जी के लिए भी है, मास के लिए भी है. So in fact, out of the 5 things, for 4 entities this becomes a scalar. Only for one quantity or one entity it is a momentum, it is a vector, and that is momentum. All right. Any questions? Please feel free to ask. Okay. So I have defined control volume, control surface, and entity. Now let's talk about advective flux of mass through S from side A to side B. I'm trying to define what advective flux is. And first I'm talking about advective flux of an entity when entity is mass through S from side A to side B. What does this phrase mean actually? The meaning of the word flux is flowing out or transport. You might have come across this word in context of electrodynamics earlier. I don't know whether this meaning actually is directly applicable in that context or not. But in context of fluid dynamics, this is how it is interpreted. Flux means transport. Transport of what? Transport of entity. But then transport, this is not only flux. Flux is just transport. But it is due to advection. What does advection mean? The word advection, this is adjective of that. This word means caused due to fluid velocity field. So fluid velocity field in general is non-zero. So fluid particles are getting transported. or moving. And while the fluid particles move, with that, there is flux of mass. If a fluid particle is, there is a controlled surface, if a fluid particle is passing, then mass is transported, there is a flux. With fluid particle, there is associated momentum. So momentum has also fluxed or transported. Similarly, energy. So all the transport that is happening, all the flux that is happening because of the background velocity field, that for that we use the word advective flux. So the word advective flux, if I expand that in a sentence, this is what it means. Advective flux of mass of fluid through through control surface S from side A to side B is the mass of fluid that is being transported across S from side A to side B per unit time, caused by what? Caused by the fluid velocity field. How much mass is crossing from side A to side B through that surface? That is what is called advective flux of mass through S from side A to side B. Unit will be kg per second. I hope you can associate that with whatever I've written here. We will use the symbol, this funny F, curled F. And I will use this subscript mass here because soon I'm going to talk about flux of momentum also. So I will replace this mass by momentum. For the time being, it is funny F mass, a scalar unit is kg per second. What will be the expression of that in terms of the background velocity field? Now on this surface, let me identify an infinitesimal area dA as shown on the figure, shaded. And I have drawn the local unit vector, local normal unit vector En, which has its sense of orientation from side A to side B. So at any point, at any infinitesimal dA, there is actually two possibilities to have unit vectors, either this way or that way, right? But then I am interested only in one direction because I am talking about from side A to side B. And I hope you will be convinced that with this description, there will be a unique choice of En. That ambiguity will be gone. You think about it at any place. So when I say side A to side B, you choose one unit vector. So that is the unit vector. So before I get this whole thing through S, I am trying to find the advective flux of mass through that small area. Okay. That is going to be this. Does it make sense? This will be the mass that is passing through. Let's first check the units. Is the unit right? Does it give kg per second? Gives. In this figure, x is the centroid of dA. So you take the local velocity, which is shown here, dotted with the local unit vector pointing from A to B, multiply by area. That gives you what? That gives you the volume of fluid. V, this part is the total volume of the fluid that is passing through that area per second. You see that? I multiply by density. So that gives me mass. That's how I am getting this. So if that is dF mass, then full mass will be what? I put double integral to denote it is an integration over a surface right here. That is the advective flux. Now this is interesting that there is a dot product here. Why there is a dot product? And at this point I can only rely on your intuition. I don't know how to mathematically further prove it. But if you have a surface, so suppose the surface, this is En and this is the velocity vector, nothing is going to pass through it, right? The mass is just going to pass over the surface tangentially. So it is actually the component of velocity in this direction that matters, that actually transports. That is why this dot product is there. Okay, fine. Then we talk about advective flux of momentum. How much momentum is passing through surface A per unit time from side A to side B? Caused by what? Caused by the background velocity field. The symbol will be this funny F, momentum. But there is another difference between this funny F and the previous funny F that I wrote. One difference is, of course, the subscript is now momentum. On the previous slide it was mass. There is one more difference. Do you observe? Sorry, underbar is there, which means generally a tensor, but in this context is going to be a vector. F mass was a scalar. Okay, I have written it here. Units, is it fine? It should be according to the definition. What should be df momentum? Any attempts based on what we showed on the previous slide? So I'm right now talking only about that shaded patch. Once we get that, then the other thing is just the surface integral. What should be the expression? Amount of momentum that is passing through that surface per unit time. That will be what? Amount of mass that is passing through that multiplied by velocity, right? So there will be one Vxt, that is the velocity, and then amount of mass. Amount of mass I already wrote last time. I'm just going to put that here. Check the units. Should be fine actually, because we had the mass thing already written. I think it's right. It is becoming a vector because of this. These are all scalars. So total advective flux to the surface is simply yes, please. That depends on what I am asking. So if you look at the title of the slide, I am saying give me the flux going from A to B. When I say that, En has to point in that direction. But there is nobody stopping you from making a query about the advective flux of momentum through S from side B to side A. You can ask for that quantity, and in that case, En has to be the other way. And that will be the negative of what I asked for. It's fine. This is okay. Advective flux of total energy through same surface S from side A to side B. The units will be joules per second. Going to be a scalar again, energy per second. This is the symbol I'll use. What should I write here? Or maybe we write directly here. I think we have done enough exercise. What all should appear here? Yeah, so लिख लिया. V dot, हाँ ठीक है, V dot V by 2, CV नहीं लाना, total energy, CVT rho B dot En D. Very good, very nice. Should be able to write such expressions. Next problem set. I have asked some questions, and on exams, these are my favorite questions to ask. I'll give you some surface, some velocity. I'll write annoying long sentences. Maybe annoying for you, but to me they make sense. Read those sentences, long sentences, and give me an expression. So you be very clear about how these things are coming. Again, xt I have not written. Everywhere xt is implied. All are Eulerian fields. Now keep this expression in your mind before I go to the next slide. Maybe you want to write it somewhere. You have already written. I'm going to ask a question, and this expression will help you answer that. My question on the next slide is that if I just say entity, पिछले 3 slides में मैंने mass, momentum, energy की बात explicitly की थी, but now I'm saying let's generalize. Advective flux of an entity through S from side A to side B. What will be the expression? I've already written that actually. I thought it was not written and I would have asked a question. But let's first look at the symbol. This is what I will call that. I will write it in this manner, F entity. In general, since it is entity, I will put an underbar here so that it can serve its purpose for all quantities of interest, all entities of interest. And mind you, this order of this tensor will be the same as the order of the entity. You see that happening? Okay. Unit will be unit of entity per second, mass per second, kg meters per second, and so on. The whole vector a whole tensor will be found in this manner, where this is also a tensor. And I've answered the question already, at least to scrutinize. I'm claiming that this infinitesimal funny F entity will be this, where phi is entity per unit volume at the centroid of T. Is it consistent with what all I wrote on the previous slide? So when it becomes energy, I've written that also. When it is mass, phi will be 1. When it is momentum, it is rho times V. And when it is total energy, sorry, mass mein rho hoga, right? Very good. Very nice. Mass mein rho, because it's per unit volume. Other things are fine. Is it clear? There is a very famous theorem in fluid mechanics. It's called the Reynolds transport theorem. We are going to derive that. The utility of the Reynolds transport theorem is that the governing equations that we want to derive for all those flow variables, like for mass, suppose there are 10 steps to derive that. When you apply conservation of mass, there are 10 steps. When you apply Euler's first axiom, there are 15 steps. When you apply first law of thermodynamics, there are 20 steps. But few steps are common for all. Say first five steps are common to all. Okay. So instead of repeating those 5 steps for each of the quantities, I would first derive the governing equation of an entity up to those 5 steps. Using what? Using phi as the entity per unit volume. And that equation, that the derivation after those 5 steps, the form that we will get, that is called the Reynolds transport theorem. And that theorem is ready to be applied for any entity later on. Okay. So it takes us halfway through the derivation journey and avoids repetition. That's what I have written here, stepping stone towards deriving governing equations of all the Eulerian flow variables of interest. So now I'm going to derive RTT and then later use RTT to derive equations. To derive RTT, the Reynolds transport theorem, I'm going to again use this figure. I'll consider this control volume enclosed by a control surface S and V fixed with respect to frame F. Motion of fluid is fixed with respect to this man, and mind you, the motion of the fluid that is being observed, that is also with respect to the same man. Of course, fluid is moving with respect to him, control volume is not moving with respect to him. First question, pertinent question to ask for RTT derivation is how much of an entity, placeholder, with phi xt as the entity per unit volume is currently inside this control volume. The units will be the units of entity itself. How much of the entity is there inside the control volume? There is flow field, of course. Fluid particles are moving, the wall surface is of course transparent. So they move in, out, fluid particles move in and out of that volume at their own will. However, if I take a snapshot, if I take a picture and ask this question at this current time, how much of an entity is contained inside the control volume? What will be the answer? What will be the answer? Use this. Start thinking in terms of this. So phi xt is what? Phi xt is entity per unit volume at this location. But that is an Eulerian variable. It means at the same time, if you go to another small control volume, its value will change. So how it should be written? It should be written in this manner. Triple integral means volume integral. Would you agree with this? I'm calling that as n. And n I should keep as a tensor because again entity in general is a placeholder. So n is the tensor, n is a tensor and it is of the same order as that of the entity itself. Now there is time sitting here. So if I change my question that how much of entity is sitting inside this control volume at a later time, in general it may change, right? Also, in a way, it depends on the location. Location of what? Location of the control volume. If there is flow in this room and I take a control volume here and I ask you how much entity is there in this at this time, that answer will be different from how much entity is there in a control volume which is here at a different x, right? Because phi in general is dependent on x and t. Now, keeping that in mind, let's look at my next question. Rate at which this amount is changing with time when the location of control volume is not changing. The units will be entity per second. I'm telling you to give you a better idea of what I am asking. And right now, I need only the mathematical expression for it. I'm not asking you why it would change. I'm just asking you to translate this long English sentence in the language of calculus. What will you write there? So I'm asking about rate of change. So there will be time d dt or del t, some sort of operator will be there with respect to time. The question is partial or something else. This is what it is. So n, as I said earlier, different for this control volume and different for this control volume. Even for this control volume, at a later time it may change. But I am not letting you change the control volume. So the derivative should only be with respect to time while keeping the locations the same. And that is why I put the partial derivative. Does it sound reasonable? Partial derivative? Okay. So this is the expression of it. Units entity per second. Now the next question is, what can cause this to be non-zero? So in general, it will be safer for us. I think I missed that and sign here. Now this is the kind of thing I'm talking about. You see, I have said this several times and yet I missed putting an underbar. But do not hold me responsible later showing this that you made a mistake on exam because of this. If I realize, I make the correction, but you should scrutinize and make this correction on your own. It is a tensor. Okay. So in general, we expect this to be not zero. Okay. But why would it change? Or rather, other words, what I am asking is, what should this be equal to? I'm trying to build an equation. This changes, but what causes that change? If you think about it, there are two reasons why it will change, or there are two types of reason why it will change. Reason 1 and reason 2, I call that. Reason 1 is the net advective flux of an entity into the control volume, caused by what? Caused due to the velocity, fluid velocity. When I say advective flux, it automatically means this. So in a way, it is kind of redundant that I am repeating this. But just to clarify it further, I thought I would put this here. My point is that since there is velocity field, this velocity field is going to bring in some entity per unit time into this at some locations on the control surface, and at some other locations, the velocity field may take out the entity. Do you visualize that happening? Right? That's what I'm calling as reason 1. So the reason why the amount of entity will change in that volume will be because of flux reason, advective flux reason, reason 1. I denote that by symbol R1. Again, in general, R is a tensor right now. What is R2? R2 is all other possible reasons. Everything else which is not advective flux, I am clubbing together as R2. Okay. Let's talk more about R2. As I said, it's the non-advective flux reason. This is one single word, non-advective flux reason. How to visualize R2? What exactly is R2? For that, I am giving you a technique how to visualize what R2 should be. For a moment, imagine velocity field has been switched off. Somehow I have the ability that I had the control volume. For an instant, close your eyes and imagine that somebody has switched off the velocity field. So the flux has stopped, but still there is some entity inside it. Now think about why would that entity increase or decrease when there is no flux? The specific answer to that depends on what the entity is. Let me illustrate this. Let the entity be mass. Imagine, close your eyes, imagine that flux has been switched off. There is some mass inside it. What could be the reason why that mass would change with time? 2 kgs था वो 2.1 होगा अगर, तो क्यों होगा? फ्लक्स तो बंद हो गया. I give you this much of mass. What decides whether this mass will change or not? Flux switched off. I give you 1 kg of mass in your hand. Classical mechanics. You know the answer. Probably it's written there also. It cannot change. Law of conservation of mass. I give you 1 kg of mass, I keep it here. Why will it change with time? Of course, if it is non-classical mechanics, then mass can become energy in nuclear reactors and all, but I'm not talking about that. I'm not talking about fission, fusion and all that. Classical mechanics, mass will not change. All right. So law of conservation of mass will give me this guidance. So this is all about guidance. I'm saying, imagine that it is switched off and then you write that. Law of conservation of mass tells me that mass can neither be created nor be destroyed, and thus R2 will be 0 for when the entity is mass. More guidance about more entities. Now suppose we take the entity to be bacteria population. This is not a primary interest for my fluid dynamics derivation, but this is an interesting quantity to look at. Suppose the water is dirty, and in civil engineering we do come across such things, right? Water treatment plants are there, very important for cities and all. So water is contaminated. Every meter cube of water has a certain number of bacteria, and you have been asked as civil engineers to write the governing equation of how the population will change with time and so on. So if the entity is bacteria population, what is the unit of bacteria population? Just a number, right? 1,000 bacteria cells. Okay, this is just a number. Guidance for R2, follow my steps here. Imagine we have been shut off. What other reason can change that number of bacteria in that? Tell me the answer, you know that. Number of bacteria, not mass. Number of bacteria. एक bacteria divide हो सकता है. Can become 2 cells, right? In that case, R2 will not be 0, but R2 will be an expression which maybe some biologist or a pathologist will tell you that it may be something like, I've just made it up, 5.6 n raised to the power 1.5. So if there are n number of bacteria, they increase their number using this equation, number per second. In that case, R2 will be that. See that? Moving on, let me quickly complete this. Come back to our more relevant quantities. If the entity is fluid momentum, answer is there, but I do want you to do this exercise. Close your eyes. We shut off. There is a certain amount of momentum which is residing in the control volume. What can change that? Laws of classical mechanics. If this book has some momentum and I want to change that momentum, what do I do? Exert a force, exert an external force, right? In other words, Euler's first axiom. That's what will govern R2 for that case, if it is momentum. So R2 will become F external. External to what? The net external force acting on the chunk of mass that is currently residing inside the control volume. That will require you to draw a free body diagram at one point of time on that control volume. Okay. Last thing here, energy. Or maybe I just don't show you that. Energy anyway, khali energy. Let's complete this exercise. What is R2? Close your eyes, shut off velocity field and tell me what will be R2. So there is certain amount of total energy inside the control volume. What can change that control? What can change that total energy? Which law will you appeal to? Well, I don't call it conservation of energy. There is a better name for that. Law of thermodynamics bolo na. First law of thermodynamics. What does first law of thermodynamics tell you? If I have a certain amount of mass, it has certain amount of energy. At what rate will this energy change? Total energy I'm talking about. Not APL 100 wala energy nahi hai. Isme internal energy mila hua hai. And you know the answer. There are two things that can change that. Rate of work done by external forces, and heat added. Those are the two things that. Last slide mein. Right. Okay. That's what I meant. Imagine we zero everywhere. Thank you. All right, we stop here. We continue tomorrow.